A second way that you can calculate free energy is by using something that looks exactly like Hess's law, where you take a few equations and you manipulate them. You turn them around, you flip them, you multiply them by a number, whatever you need to do in order to reach a target equation. You add your equations together, you add your changed delta g's together. Remember, if you flip it, you have to change your sign. If you multiply your equation by a number, you have to multiply delta g by the same number. Then when you add them together, you get your overall delta G. It works just like Hess's law for enthalpy. And then a third method that we can use to calculate free energy is this wonderful equation right here, which looks like the exact same one that we just saw for entropy and looks like the exact same one that we saw later for enthalpy. And so you can use the same equation 3 different times for any of these 3 thermodynamic functions. Just like with enthalpy, the delta G, the change in free energy of formation for an element in its standard state, is going to be 0. This is a little bit different than entropy. Remember, entropy, elements do not have 0 entropy and at standard state. But free energy and enthalpy are both 0 for an element in a standard state. So let's take a look at an example problem like this. Our first problem, letter A, has us calculating the change in enthalpy using bond dissociation energies. Now, you may not remember this, but we learned that you could use the bond dissociation energy to find enthalpy changes by using the equation bonds broken minus bonds formed. So to do problems like this, it is sometimes easier to draw out the structures of the compound so you can see which bonds are being broken and which bonds are being formed. So I'm going to go ahead and do that. So if I look at these structures, I see that bonds are being broken here and here. And I see that bonds are being formed here and here. So I'm going to put in my bonds broken and then minus my bonds formed. So here's my bonds broken, a CH and a ClCl. And here's my bonds formed, a CCl and an HCl. And I get negative 151. The unit here is going to be the same unit that was in these bond energies. Up here is going to be kilojoule per mole. And then for our next problem, it wants us to calculate delta S. Well, all I've got is I've got delta G's up here, and I've got the delta H that I just figured out. So if I've got delta G and delta H, and I want to find delta S, I'm probably using this equation here. Now what I've got though is I've got delta H for the reaction. That's what I just calculated. I'm trying to find delta S for the reaction. I do not have delta G for the reaction yet. I've got delta G's of formation. So I can go back and use this equation from up here to use my delta G's of formation to find my delta G of reaction, and then I can go to this equation here. So let's start with the delta G's of formation. Plug those in. Okay, so here's my equation here, and then if I go through and solve this, I'm going to get negative 115.1. The units, or whatever these units are up here, so that's kilojoules per mole. And now that I have this, I can go ahead and plug these into this equation here. And we get negative 1.2. The unit here is going to be the same as the units for delta G and delta H. It's going to be kilojoule per mole Kelvin. That Kelvin's in there because of that Kelvin temperature. Usually this is written in joules per mole Kelvin for enthalpy. You don't have to do this unless it particularly asks you to, but that's how it's usually written.